Hello, everyone. Thank you so much for joining today. It looks like there are a few more people logging on. We can give them just a little bit of time to get logged in. My name is Shannon Holmes. I'm a medical physicist here at Standard Imaging. And it's really exciting actually today to be able to talk to you about the Exradin A30 ionization chamber. This is a project we've been working on to try and provide an option for NIST traceable dosimetry for ultra-high dose rate flash beams. We have a little bit of housekeeping to keep or to get out of the way before we really get started. In case you haven't been on one of our webinars before, we do record these webinars, and you'll get a link to the recording a little bit later on. Our normal lady who does all of that is out on maternity leave, so we're a little slower than we normally would be, but we will get that link sent out to you. If you have questions as I'm going through my slides, feel free to type them in anytime in the question and answer dialog box within Teams. And if you're listening from another country, you'd like to, or just are not a native English speaker and would like to have live captioning in your own language, Teams has that lovely feature. So go ahead and set that if you'd like, but please don't change the spoken language or you'll mess up the transcripts for everybody. So with that out of the way, I also have a few acknowledgements and disclosures that I'd like to make with regard to this project. We do have a patent pending on the A30, and the development project has been funded in part by a couple of small business innovation research contracts through the NIH and the NCI. And as part of that research, we have a couple of teams of research collaborators at MD Anderson Cancer Center and at the University of Wisconsin. And we're extremely grateful for the help and the input that they've had into this project and into validating the ionization chamber, performing calculations and making measurements and providing some wonderful feedback on our projects. So for those who are less familiar with ultra-high dose rate radiation, I'll give a brief introduction to flash. I promise it'll be brief. There are a lot of details that I will admittedly skip over here, but to try and just set the stage, if this is not really your area. Ultra-high dose rate flash radiation has been shown to provide equivalent tumor control with decreased normal tissue complications compared with conventional dose rates. So this was really brought to the fore recently, I guess it's 12 years ago now, but with an investigation published here, I show the link by Favadon et al., where they were looking at the difference in lung fibrosis between mice who were irradiated with ultra-high dose rate radiation versus traditional radiation. And there was a drastic decrease in the normal tissue fibrosis in that ultra-high dose rate irradiated cohort. This sparked quite a lot of excitement in the field of radiotherapy, with a key question of if these ultra-high dose rates are going to spare normal tissue while still providing the same sort of tumor control, is there a chance that we can potentially push doses higher to get improved tumor control without increasing our normal tissue toxicities? And of course, a whole bunch of different investigations ensued. There's a lot of detail that has come out in the past 12 years following that Favadon manuscript that has indicated that this is a very complex issue. The exact cause, there are a lot of suspects, but there is no smoking gun on the exact cause of why this flash effect, this normal tissue sparing occurs. There's got to be a threshold somewhere between what we see at normal dose rates, traditional dose rates, and this effect at ultra high dose rates. So that threshold is mostly understood, but still a little bit unclear. And some of those studies that I won't go into indicate that threshold may be slightly different depending on the type of cancer you're talking about and the end effect that you're actually using as the measurement of that normal tissue toxicity. So some toxicities, some different tissues are responding more or less positively, I guess, to that ultra high dose radiation. All of that aside, From a dosimetric standpoint, what we really need to know in these ultra high dose radiations is the dose. We need to know it very accurately, especially as we're trying to compare between different studies done at different places with potentially different irradiators. But the key point is that if we're delivering extremely high doses in a fraction of a second, there's not a lot of room for error, and there's no space to kind of make up for differences later on in the treatment with other fractions. Yes, there is a little bit of investigation there is investigation into fractionated flash irradiations, but those are to my knowledge, generally limited to just a handful of fractions. We're not talking about 30 or 40 fractions like we are with some traditional treatments. Existing ionization chambers have significant recombination and saturation effects that occur in these high dose rates that make them suboptimal in terms of the accuracy of the dose measurement that's needed for real clinical treatment. So other dose rate independent or dose per pulse independent detectors have been used for these dose calibrations. Some examples are listed here: radiochromic film, alanine, TLDs, OSLDs. They're calorimeters. There are a couple different flavors of calorimeters that have been used for flash beam calibration. But for a medical physicist like myself, the ion chamber really is still the detector of choice for standard clinical use. It's a simple device. It's an active device. It gives me a result immediately. I understand a lot of how it works. I won't say that I understand everything in these extremely high dose rates, but they can be calibrated. They can be given a dose conversion factor that is traceable to national standards. So we have some good link with the actual dose that's being delivered when we're measuring with these ionization chambers. So our challenge with this project was to create an ionization chamber that had minimal saturation at high dose rates and can still be calibrated at a dosimetry calibration lab so that you can get that NIST traceability. A little more detail on why the existing ion chambers don't work. There's a very high recombination problem with ultra high dose rate radiation and these ionization chambers. You create very dense ionization tracks. If I have my simple schematic of a parallel plate chamber, I have a negative polarity on one side, positive on the other, and the air gap in between. Radiation traveling through here causes that ionization. And in general, these positive and negative ions would then be pulled towards the opposite polarity electrode. When this track gets extremely dense, your nice uniform electric field within that ionization chamber starts to have little pockets of perturbation, differences in the electric field based on the density of these ions that are created. That gives the ions a little bit less of a pull, decreased pull from the electrode, and allows them to recombine before they're collected. So there's initial recombination that happens right there, and then volume recombination that happens as the ions travel through the ionization chamber. This phenomenon of the perturbation of the electric field is called self-shielding of the ions that prevents that collection. The larger your plate separation, the larger your problem because of the distance that those ions have to travel and the density of the tracks. There are also some limitations that come from your electrometer as you're measuring with an ionization chamber. So we're with a really high dose in a very short duration, a single pulse of high dose per pulse radiation. You have an input signal that is essentially a delta function. It's a very sharp increase followed by an extremely sharp decrease. This is also sometimes called an impulse. That high instantaneous current that appears and then disappears is not handled perfectly well by the electrometer. This is a hand drawing, so it's obviously exaggerated, but there's some response time of the electrometer, and then there's a decrease as the charge is cleared from the electrometer itself. So that also has to be considered when you're looking at high dose per pulse measurements. In terms of the beams that are available for flash radiation, proton beams were the first ones that were used for these investigations, mainly because proton systems at the time were set up such that the pulse repetition frequency could be increased. And you could get a high dose rate by just shooting more pulses through your accelerator. This actually results in what's called a quasi-continuous beam. The pulses are so close together that it, from the measurement standpoint, it acts like it's just a steady irradiation. Now, there are some differences in proton systems depending on your accelerator. So you may have some fine structure within a larger macro pulse if you have what are called pulse dumps. But in general, from a detector standpoint, this still acts mostly like a quasi-continuous sort of a measurement. It's not that super sharp impulse that we get with a single high dose pulse. For electrons, those systems are generally set up to deliver extremely high dose in individual pulses. So only a few pulses are given, and each one of those has a very high dose, which results in an extremely high instantaneous dose rate within those very short pulses. Photons as the third option. I mean, that's very common in radiotherapy, but in flash, it's harder to get to those extremely high dose rates. So I know there are preclinical systems for photons. I admit I have not followed this probably as well as I should have. I think they are also quasi-continuous, but at the time of the main development work on the A30, we did not have a photon system available to test on. So that'll be a fun place to expand into as those systems become more widely used. Electrons are the biggest challenge for ionization chambers to handle in this ultra high dose rate regime because it's that ultra high dose per pulse and because it's that instantaneous, nearly instantaneous delivery of a lot of dose. So that's where we were focusing our development work because if we can handle this, we can handle the others. Just because it's an easier problem from first principles, from the basic functionality of the ion chamber. So in designing a chamber, we were looking at prior publications which proposed ultra-thin parallel plate chambers as a possible solution. We did investigate other shapes as well, but the ultra-thin parallel plate chambers really are the most promising, or were at the time. We did the 1D MATLAB calculations just to confirm that what was in the publication was what we were predicting as well. And yes, they confirmed that hypothesis, at least in that simple 1D model. In terms of constructing ultra-thin parallel plate chambers, there are a number of challenges that come along with that as well. If you're building something with extremely small separation between your electrodes, you have to have perfectly parallel and very smooth surfaces. If it's not parallel, then it changes the volume. It can change the recombination. If you have burrs on the surface, you can actually cause shorts within your ionization chamber, all less than ideal functionality. You need extremely accurate plate separation. If you can't maintain the same plate separation, not only across the chamber itself, but from one chamber to the next as you're constructing them, now you're going to have if you don't do that, you're going to have chambers that don't respond the same way because the response is somewhat dependent on that plate separation. In terms of material selection, we really like to use our conductive plastics because there are no high Z materials. They have a high dose resistance, but in terms of the insulators as well, we wanted to make sure that we weren't introducing some additional energy dependencies or inadvertently causing issues with the chamber by introducing materials that might have an energy dependence. So we're trying to stay away from high Z materials in the construction. And then in designing it, chamber volume is an important parameter to consider as well. And if we're constrained by our parallel plate chamber having a specific separation, the only way we can change our chamber volume is by changing the electrode diameter. So we were looking at some different diameter electrodes as well. We wanted to make sure that we had a large enough signal to be able to calibrate this at an ADCL, and yet have a small enough chamber that we can, as much as possible, avoid electrometer saturation as we get into those high doses. So The chamber signal is dependent both on the dose that's being delivered and directly dependent on the volume of the chamber. So if you double your volume for the same dose, you double your signal. And last but not least, we wanted to make it waterproof. Not just because water is the medium we like to use for dose calibration, for reference doses, for commissioning beams, for all of that. But water also can help handle the heat. When you're delivering that much dose, it creates a reasonable amount of heat as well. And the water can help protect the chamber, help dissipate the heat somewhat. So we started with a prototype investigation. The next few slides, I have images, both these chamber images and some plots that are published in this manuscript by Liu et al. So if you want to go look at that later, here's your reference. But our first challenge was investigating what could we construct, and how thin did we actually have to make this parallel plate chamber. So we started with essentially our A11 chamber as a base, and we made multiple caps for it. So this chamber didn't actually have steps in the cap like this. This is just to represent that we had 6 different caps to create chambers with this different gap. So with that investigation, really, it looks like the 0.3 millimeter gap was going to be the best functioning as well as most reliable construction. We looked at the electric field strength that should be used with that chamber, and you can see that here around 12 to 1500 volts per millimeter, we start to get into some charge multiplication. This is showing the values for each of those different configurations of the ion chamber. These are the air gaps that we were investigating. But all of them at about 12 to 1500 volts per millimeter would start to slip up into the charge multiplication region. So we knew we wanted to operate as high as we could without getting into charge multiplication. So we're looking at operating with electric field strength somewhere in this range, 1000 to 1200 volts per millimeter. The next prototypes we made were just a fixed gap prototype that matched that same electrode diameter that we had with the initial prototype. So it's a 20 millimeter collecting electrode diameter. And then we made one with a smaller electrode diameter that matched our A10 chamber, was based on that construction model. And that has a 5.4 millimeter diameter collecting electrode. So you can see the volumes of these chambers are essentially an order of magnitude different. So you get a factor of 10 lower signal from this A30 design than we did from the prior prototype design. We revisited the electric field strength to make sure that things were still performing as expected with this new smaller diameter collecting electrode relative to the one we had investigated previously. And it did a little bit better, even up to 1500, and then started drifting up into charge multiplication. But looked like behavior should be nicely stable right through this region. With that 1D MATLAB model for charge collection efficiency, we had a prediction of what we thought the charge collection efficiency should be for that 1000 to 1200 volts per millimeter. So we measured it as well with those 2 prototypes. And with the larger diameter prototype, things started drifting down a fair bit sooner than the model predicted. This could be partly due to electrometer limitations, but obviously was less than ideal for the chamber that we were aiming for. But the smaller diameter prototype showed excellent charge collection efficiency up into the 4 to 6 gray per pulse range before starting to dip down, but was still above 90% when we were at 9 gray per pulse. And this, I believe, was a 4 microsecond pulse. Looked at pulse repetition frequency for that smaller diameter chamber as well, and saw nicely stable behavior for a range of pulse repetition frequencies. And then pulse width we looked at as well for different doses per pulse, a range of pulse widths, and we saw a nicely consistent behavior for that range where we knew there wasn't a decrease in the charge collection efficiency. And then, of course, we looked at those lifetimes. So with that initial prototype design, we delivered about 300 kilograms. This was the smaller diameter prototype. Sorry, I should have been clearer about that. Initial A30 prototype design. We delivered about 300,000 gray over a period of months. And we were monitoring the leakage values in particular because those tend to show the dose degradation sooner than some of the other parameters for the ionization chamber. And things were looking good. So we said, all right, let's do another 300 kilogray and see how it goes. There was a slight misunderstanding, and that 300 kilogray was delivered in a single session rather than over a period of time. So as you might imagine, we created a lot of heat with that, and we melted our chamber. It really, some of those plastics became so rigid and brittle that they just crumbled. You can see here, we learned a few interesting things from this mishap, though. You can see this was the buildup cap that was being used. And then this is actually the electrode from inside the chamber, also showing that nice non-discolored shiny black that we expect to have from the newer plastic or the non-damaged plastic. But this insulating plastic that we were using for the body of the chamber and the stem of the chamber at the time, you can see right where that radiation field ended. And just how discolored and of course shattered this was. The stem itself did fine once it was out of the radiation, but there was major damage here. So we learned from that there were actually some insulating materials inside that chamber that survived just fine, slightly different plastic. So we replaced the body of the chamber with that insulating plastic instead, in order to increase the dose lifetime in the commercially released chamber. So the updated chamber design then had that replacement of the lower dose tolerant non-conductive plastics with a higher dose tolerant plastic in order to improve the dose lifetime. We were able to implement a waterproof construction design at that time as well. So this chamber can now be submerged just with no sleeve, no concerns on that. We added this nice alignment line on the outside because it's a slightly thicker entrance window than some of our other parallel plate chambers. It really does help to have that alignment line for setup purposes. We've worked with our research collaborators to perform the beam quality correction factor calculations and measurements to corroborate those. And we've sent multiple chambers to the University of Wisconsin ADCL, where they've been able to give us dose to water calibration factors, TG51 dose to water calibration factors, just following their normal process, which is what we were aiming for. And then with this final design, we wanted to just reevaluate some of the key performance features to make sure that in changing just some of our construction methods and adding the waterproofing, nothing changed in terms of the materials right there at the active chamber volume, but some of just the way the construction was done. We wanted to make sure that we hadn't changed anything, so that all the prior values would still be valid. So we looked again at the dose response, and we pushed it all the way up to 34 gray on this one, and had nicely linear dose response. This was done using a range of 1 to 20 pulses, with instantaneous dose rates here of 4.3 times 10 to the 5th gray per second. And this is becoming a more interesting factor to track in terms of chamber response. So we didn't do as good a job with the initial paper manuscript that I was showing excerpts from before. This is something that I think is going to be more interesting for researchers to track going forward. So we're trying to do the same. We looked at pulse width linearity with pulses ranging from 1 microsecond to 4 microseconds, again with that fixed instantaneous dose rate so that we're not adding another complication in that measurement. And it was obviously nicely linear. And then for charge collection efficiency, the commercial design matched the prior prototype performance. We were still 95% charge collection efficiency at 6.2 gray per pulse, again for that 4 microsecond pulse width that we had used in the prior investigation. It did drop to around 84% at 12 gray per pulse. The prior one I said was staying above 90 at 9 gray per pulse, so we're still right on track with the way that curve looked. But I'm again plotting it here as a function of the instantaneous dose rate. And I think that we'll be tracking some things based on instantaneous dose rate a little more carefully in the future. So to summarize, we have with the A30 a parallel plate design with 0.3 millimeter plate separation. That's 3 human hairs. It's very small. It was a fun challenge to work on, but we've got a nicely consistent construction method now. We've validated that with the calibration factors even from the ADCL. Because that's so chamber volume dependent, variations in the calibration factor can tell us a lot about variations in our construction method. So that's nicely worked out now. It does use our C552 conducting plastic, so they don't have high Z electrodes. It is waterproof, so you can put it straight into your water tank for measurements in your flash beam. And it is capable of functioning in both traditional beams and flash beams, which is what has enabled us to provide that pathway for NIST traceability between the standard cobalt calibration and your ultra high dose measurements. We believe we've got a high dose lifetime on this. We have not repeated the massive dose for destructive testing. But we are monitoring doses to see just how long the chamber will last, and it looks like it has a nicely high dose lifetime. We do have a manuscript in process with those beam quality correction factors and measurements, so I'm not sharing that here today, but hopefully very soon we'll have that submitted and hopefully get through peer review relatively quickly. But I would expect to see that published later this year. I wanted to tell you it was released. All the paperwork was done before the holidays, but between vacations and some other stuff that's outside my control, it's still undergoing the final sign-off. It will be commercially available before the end of the month. You'll see it appear on our website once that's been approved and fully signed off on. But if you're interested in it right now, you can certainly reach out to your salesperson and ask for a quote. We just haven't made that publicly visible on our website yet. So with that, I'm happy to take questions. I'm sorry I have not been looking at the Q&A at all as I've been going through this.
Shannon, you have 2 questions.
Okay.
So would this work with a UHDR synchronocyclotron proton measurements?
Yes, so we've done some proton measurements with it, and it works fine with protons.
The other question is, what field size is used for calibration? Also, how well does the material outside of the chamber but inside the chamber field hold up as a function of dose, measuring that the longevity of the chamber is the entire system, not just the chamber itself?
Yes, absolutely. So that's the field size that's used for calibration, I believe, is a 10 by 10. It's the standard TG51 calibration field size. The material outside the chamber, the stem of the chamber and the body of the chamber, all of that have been swapped out for the higher dose tolerance non-conducting plastic. The limiting factors in the stem of the chamber is actually most likely going to be the insulators within the triaxial cable, and so that's not something that is easily swapped out on our end. But the full chamber system, including that cable, we expect to last more than that 600 kilogray that we were looking at with the other chamber. Good questions, though. Thank you.
There's nothing else in the chat, Shannon.
All right, in that case, I'll thank everyone again for coming. I really appreciate that you took time out for this. And please reach out if you have questions, or reach out to your salesperson if you're looking for a quote. Thank you so much.